In this part of the lecture, we will discuss about different earthquake design philosophies and equivalent lateral static force procedure. We will also go through some of the other procedures that is recommended by the building codes in order to design the seismic design of building structures. First of all, design of structures to withstand the maximum density of earthquake or earthquake-proof structure is highly expensive and may not be possible. We always go for earthquake-resistant design. That means that to design any structure, which we can say it can be an earthquake proof, it's not possible because it will be very highly expensive and it will be uneconomical. So we always go for an economical design which can be earthquake resistant, which can bear a certain amount of earthquake energy, and it can dissipate energy, but it will not collapse under such earthquake. So these are the main part of this earthquake engineering philosophy. There are different performance levels of a building structure. One, that it is fully functional after an earthquake, it is operational after an earthquake, life safety, that it means it is damaged but the life inside the building, lives of the occupant is safe, and there is near collapse or collapse prevention, that it is the building is standing, it is not collapsed completely, but the building is standing and the occupants have enough time to evacuate from the building, so they can easily save their lives. As we can see in this table, fully functional, that no significant damage has occurred on the structural and non-structural components, buildings suitable for the normal intended occupancy and use. In operational, no significant damage has occurred to the structure, which retains nearly all of its pre-earthquake strength and stiffness. Non-structural components are secured and most of them are foot function. Okay. In life safety, occupational damage to structural elements with substantial reduction in stiffness, however, margin remains against collapse. Non-structural elements may be secure but may not be function. Occupancy may be prevented until repairs can be instituted. Similarly, near collapse, substantial structural and non-structural damage, structural strength, stiffness substantially degraded like the margin against collapse, some failing debris and hazard may occur. So these are different performance levels in which we see a building after an earthquake, that it can be a fully functional, that the earthquake was not that strong enough, and the building is well designed, it is fully functional even after an earthquake, a predicted earthquake. And operational, that no significant damage has occurred, and then there is life safety and near collapse prevention. We use different performances of building structures to design our buildings against seismic or earthquake forces. There are different analysis procedure in order to analyze the building structure and then to design it for earthquake resistant structures. There are structural model. One is linear, another is non-linear. Linear, our stiffness, Young modulus, area, cross sectional area, moment of inertia, geometry, they are all constant, and hence they produce a stiffness matrix of K, which is also constant. So in linear model, it follows the simple Hooke's law, that F is equal to Ku. So this will not change. However, for the non-linear model, the property of a building structure or characteristics of a building structure will change at every force that we apply. The displacement will depend upon the real-time stiffness matrix and displacement matrix of the structure. So this structures stiffness, moment of inertia, and of a building structure will not be constant. So then for seismic loadings, we can divide the loading into two parts. One static, another one is dynamic. So one is equivalent lateral force procedure, which is also known as static lateral force procedure. This is mostly widely used in the design of structures. Then response spectrum analysis procedure, and then linear response history analysis procedure, which is linear time history analysis, direct integration, or linear direct procedure. And then in non-linear procedure, we can also have non-linear static pushover methods, and then non-linear response history analysis also, and non-linear time history analysis, non-linear direct procedure, and direct integration. So these are the method to solve non-linear model, and these are the method to solve the linear model structures. Linear model structures, if you design a model by default in any software like Perform 3D, SAP, or ETAB, or Save, Stat Pro, the structure is linear by default. You have to provide the non-linear properties to the building structures. Even if you provide the large amount of force on a building structures, it will give you a large displacement, but this will be unrealistic in case of an earthquake, because there is a certain limit at which the building can bear the forces and displacement. So it has to be restricted at certain point where it will definitely have some cracking and it will collapse. But this phenomena is not shown in the linear model. However, in a non-linear model, we can predict, we can provide some hysteresis, we can provide some behavior of the material and cross-sectional areas, so that it can act when the our member is yielding, when our building is going to the collapse or collapse prevention, or when our building is moving towards in the ductility part of the building structure. So this is a different procedure, so it is a little bit more complicated, but this will provide us a more accurate results. For seismic design, there are different codes that we use. The Building Code of Pakistan uses the seismic provision, which is provided in the UBC UBC 97 Uniform Building Code, and there are other codes which provides the minimum design load associated with criteria with building and other structure, which have a chapter for seismic design, which is ASCE, American Society of Civil Engineering 7-16. And then there is also for steel similar code for seismic design of steel structures also. So different. Then we have Euro code also, Japanese code, and Korean code, and definitely New Zealand and Australian code. There are different localized or regional building codes which we use for the design of building structures and seismic design of building structures. Building Code of Pakistan is also one of the regional codes. However, like American Society of Civil Engineering Code, ASCE 7-16, or latest one, or and ACI, they are widely accepted by the different countries in the world. So, in order to determine the lateral forces on a building structure, we need to perform some analysis, which can be dynamic lateral force procedure or static lateral force procedure. Static lateral force procedure is one of the most widely used in practice. However, dynamic lateral force procedure or dynamic analysis method, in which we have response spectrum analysis and time history analysis, are required for irregular structures or important building structures, or very important structures like nuclear power plants and main facilities like large hospitals. And we have to see the seismic response is which can be also dominated by the different modes other than the fundamental mode. These procedures are more tedious and difficult to perform. So they are used for irregular buildings and other types of buildings, which are very important. However, for static lateral force procedure, we take all the base shear that act on a building at the base of the building, and then we apply the simple static forces on different levels of the building structures. We will briefly go through each one of them. Time history analysis. In this, we take an actual ground acceleration in different components x, y, and z, and then we apply on a structural model. It can be linear structural model or non-linear structural model if we have provided the non-linear properties of the building structures. And hence, after applying the ground acceleration, we evaluate the different lateral displacements of the building structures, stresses and forces that is induced due to that ground acceleration. These ground acceleration can be of past earthquakes, and they can also be of artificial created earthquakes. So this is basically known as time history analysis, in which we provide acceleration, different acceleration at different time period, and then we implement those acceleration in the structures which induce the forces in the structures, and it causes the mass of the structures to displace or deform at different position, and hence we get the response. These procedures are very time consuming, and rigorous analysis are required for these types of procedure, and the model should also be developed very carefully. But the good side that it provides very accurate depiction of the response of the building structure. Another type of analysis is dynamic lateral force procedure, is response spectrum analysis. In this, we have a 1 degree of freedom system in which there is a mass and it have some natural time period, and then we apply the time history record and we obtain the maximum displacement for this structure. Similarly, at different time periods we have different maximum displacements, and we record these displacements uh, as compared to the spectral acceleration, and these peak displacements can be further plotted in this curve, and this spectral response spectrum can be applied. The spectrum of these displacement and time periods can be applied on a building structures to evaluate its response under the seismic loads. So this is another type of static, and there is between static and dynamic procedure to analyze the structure under the seismic loadings. This is a response spectrum analysis which is based on UBC 97 curve, and it have provided the codes, and we have different values for different site conditions, and then we can plot this curve and apply on the building structures to calculate its response. Static lateral force procedure. So this is the equation to calculate the base shear provided in UBC 97. V is our base shear, C is seismic coefficient, and W is seismic weight of the structure. CS can be calculated using CVI divided by R into T, and this can all be written as this form of an equation. In this T is the time period of the structure, which is not the classical model damping model analysis time period, rather than it is a approximate or time period from an approximate empirical formula. R is response modification factor. It is also called overstrength factor in UBC 97, and it is provided in the table, and this will be the numerical coefficient representing the inherent overstrength and the ductility capacity of the lateral force system. And CI is the importance factor of the building, and this is also provided in the table. And CV is seismic coefficient. In this CV we incorporate the soil parameters also, and also the seismic hazard level. So the zone like zone 3, zone 4, zone 2AB, and soil type, like different soil types, will be incorporated in this coefficient, and then we can calculate this CV, and after calculating all these parameters we can calculate CS, which is seismic coefficient, and then further we can calculate our base shear that will be applied on the building structure. So on the basic equation of the UBC 97, there are some limitations that the code has prescribed to design the building structure using static lateral force procedure. So the total design base shear need not to exceed V is equal to 2.5 into Ca, which is seismic coefficient of acceleration, I divided by R into W. So this is the maximum base shear that we need to consider. So this base shear is maximum, and the total design base shear shall not be less than V is equal to 0.11 Ca I into V I into W. Then this is the minimum base shear, that the lateral force in any condition should not be less than this coefficient and this value. So in any case, I mean, uh, whatever our building type is and whatever our soil type is, we need this amount of base shear to be applied on the building structure. In addition to these two limitations, so for seismic zone 4, there is a special provision to which we provide the minimum base shear, and this is 0.8 into Z into NV into I divided by R into W. These two factors, Z and NV, is basically the zone effect of the site is incorporated in the formula, and this is especially for seismic zone 4, that the minimum base shear should not be less than this one. And NV is a near source factor, that how much our building site is uh, from the source of the earthquake. So if it is less than 10 kilometers, then there is a special directivity effect on the building structure. It is a different kind of effect, that when our building or site is close to the rupture or close to the earthquake, there is a different response in the building structure that need to be incorporated for the response of the structure. So in order to incorporate that effect, we need to incorporate these two factors in design of building structures using static lateral force procedure. So these are the limitations of UBC 97. So in order to calculate the time period of the structure, these are the approximate formulas that is provided in the UBC 97. So there are two methods. One is relatively simple as compared to the method 2, which is a little bit more complex. In method 1, the formula says T is equal to, time period is equal to Ct into Hn, which is the story height of the building structure. And to calculate the Ct, we have different coefficients. This is for steel moment resisting frame, for reinforced concrete moment resisting frame, and for all other buildings we can use this coefficient. And alternatively, for the building structures which have a shear wall, we need to calculate another term, which is 0.1 into AC, where AC can be calculated using this formula. uh, in AC, this AE is the minimum cross-sectional area of a shear wall, and this DE is the length of the shear wall in the direction of the lateral forces being applied. And this ratio should not be greater than 0.9, which is mostly the case, because the width of the shear wall will not exceed the 90% of the building height. So after calculating this, we can simple calculate the time period of the building structure. And second formula is T is equal to 2 pi under root summation of all the weight of the building structures at different stories. Wi is the weight of a story at ith position, and then we will calculate the displacement, which will be calculated from the static forces applied on each forces, and then we can calculate another vector, which is the displacement. And then after inputting all the values in this formula, we can calculate the time period. It is much more accurate approximation, but mostly this is not used in practice. However, we will be using method 1 for the design of building structures. These are the steps to calculate the base shear for the static lateral force procedure. So in first step, first of all, we have to find the site specific details in which we'll be our zone factor, and then we will have to calculate which type of site is it, site 1, 2, 3, and then we will calculate their values of NA, near source factor values, and NV factor also, and then we will calculate the seismic coefficient, which is Ca, Cv, and further we will calculate the importance factor of the building, and then we can calculate the response modification factor or overstrength factor using the tables, and finally we can approximate the time period as we have seen in the previous uh, slide. Finally, we will calculate the total base shear and then apply the codes for maximum and minimum limits as we have seen in previous slides. Then in the last part, we will distribute these forces along the building structure, and then uh, check for and design for those forces. So the forces that we will get from these little static force procedure will be basically our seismic demand or seismic forces for the design of structure. Now, in order to calculate the base shear, first of all, we need to classify our seismic zone, and then we need to calculate, and then we have to check our soil type and past earthquake magnitudes required for high seismic zone, and the distance from the rupture or the seismic sources for past. So we can evaluate the NVNA for near source value for zone 4. So in site specific details, these are the things that we need to calculate. This map shows different zones of seismic zones of Pakistan, and these red one are seismic zone 4, and this orange or yellowish type shows the zone 3, and green shows the part of the country which is in zone 2B, and similarly zone 2A and zone 1, which is least seismic zone. And regarding these zones, we have different Z factors, which is shown in this table 16.1. So in order to evaluate our soil type, we have a table which is soil profile types. In this, soil type can be classified into from SA to SF. There are different soil types, and to evaluate your soil, you need these three different parameters, or any of these three different parameters to evaluate your soil type. This is shear wave velocity at 30 meters depth, and then we have standard penetration test value or SPT value, N value, or we can calculate the undrained shear strength of the soil. If the shear wave velocity is greater than 1500, then we have hard rock, or then similarly rock, very dense soil, or soft rock, and then stiff soil, and then soft soil. SF is a special provision, and for this we have to go for required for the specific site evaluation. As we see that from SA to SF, our soil get from stiff to less stiffer soil. And if the soil type is unknown, it is typical to take SD for the soil type of the normal structures. And for past earthquake magnitude, this is required for seismic zone 4 to decide the seismic source type, so that obtain the certain coefficients. In order to do that, we have different seismic source types, which is type A, type B, and type C, and which can be classified using different magnitudes and slip rates. And using this values from the past earthquakes, we can evaluate our source type of size of earthquake in these three categories. And then further, to calculate the seismic coefficients for seismic zone 4, we have these factors, which is soil type profile, Z factor, and then Further, we can calculate the SV factor, which is seismic coefficient for velocity. And similarly, near source factor for velocity, we can calculate seismic source type, which can be classified from less than 2 kilometer, 5 kilometer, 10 kilometer, and greater than or equal to 15 kilometer. And similarly, this is the seismic coefficient for acceleration, and we can calculate the values from of Ca and Na from these value for size, especially for seismic zone 4. This table shows the occupancy category for different building structures or structure type. Like it ranges from 1, which is for standard occupancy occurrence, like all other structures uh, having the function not listed in these categories. Then we have some hazardous facilities like gas power plants, nuclear power plants, or explosive, which can come under this higher importance factor than 1, which is 1.25. And then we have other essential facilities. They should also be designed for higher importance factor. So after selecting the building type, you can calculate the I factor to evaluate the base shear of the structure. Now look at the table to determine the R factor or response modification factor. And in table 16-N, we can find response modification factor and another factor, which is omega, is called structure over strength factor. This is used to amplify the design forces for certain elements, which is intended to remain elastic. So the response modification factor is basically we reduce the value of elastic forces to a certain level of design forces, and then we design the elements at that position, and we allow certain elements to get shielded and go into the ductility region of the structure. As we can see in this, the special moment resisting frame has a very high response modification factor, 8.5. This means that we are reducing the elastic forces by the factor of 8.5. The R factor should be selected very carefully, because for response mode, for special moment resisting frame, the detailing requirement for the seismic design is very important and very difficult. So we need to provide proper detailing if we want to qualify our structure as special moment resisting frame. And if not, then if not, we are not very careful about the detailing, then our structure will be ordinary moment resisting frame, and for this it's almost 3.5. So that's why we have to be very careful while providing the detailing for beam, column, flap, footing, shear walls, and any other element of outrigger structures or any other element of the structure. So we have to be very careful while selecting the R factor. And similarly, over strength factor, it varies from 2.2 to 2.8, and this is basically used to increase the design forces for certain elements in a structure which we do not want to yield under any circumstances, like shear walls or like transfer girders. So this is another important factor. So this is the table to determine R for static lateral force procedure. So as we have discussed, R factor basically reduce the base shear to make the system economical. Our structure will suffer some damages explained in the earthquake design philosophy, as we have discussed in the previous slide. For structure exhibiting good performance, R factor will be high, as we have discussed about the special moment resisting frame. Uh, by providing the adequate detailing of the structure, we can increase the R factor and the structure will become more economical. Calculation of time period. As we have discussed, there are two methods for approximation of time period. One method is this, and these have different factors for different structures. Another method is a little bit more complex, but we will use the previous method. We have discussed these both methods in previous slides. And finally, we are at the point where we have to calculate the uh, amount of base shear which will be applied on the structure. So these are the equations, and this is the total base shear to calculate for zone 4, and these are the equations to calculate the base shear and other seismic level, and these are the limits, as this one is also have been discussed before. The final step is to distribute the shear forces along the height of the building structure. So in order to do that, first of all, we will use this formula, and in this we have to calculate the forces at each story level x, and we can calculate using this equation. In this equation, this Ft is the additional force that is applied at the top level, that is roof. In order to calculate that, in the formula for Ft is equal to 0.07 into approximate time period and total base shear for time period greater than 0.7. If it's less than 0.7 or equal to, then Ft will be equal to 0. For Ft to be, Ft is basically used to incorporate the effect of higher modes in a building structure. Because when the time period is higher than 0.7, this means the structure is low rise to mid rise structure, and we have to incorporate the effect of higher modes also, because using this formula we will have a kind of a triangular forces applied on the structure. So but this will represent the seismic forces for the future earthquake also. But in order to incorporate the effect of the um, higher modes effect, we need to use this Ft to apply to have additional forces applied at the top level. So after incorporating Ft into this formula, we can calculate the forces at each story level. Wx is the seismic weight of the that story. Then hx is the height of the story, and this is the summation of total seismic weight and height of the building structure. Seismic weight, we have to include dead load and 0.25% of live load of the structure. So this is how we distribute the shear forces along the building structure. So after this we will perform some numerical in next video.